start recording. All right. Okay, so yes, last time we did the camera zooming thing, and this time, so we're going to finish up the line drawing, and we had, so you remember we had like a thing where we had a start point and an end point, and we took our like, we had a 1x1 pixel, white texture, which I've drawn in red, and we took it and we like placed it there, and we rotated it and we scaled it up so it, filled out that section there, and that's how we got our lines, with like thickness T or something to that effect.
Yep.
So that should all be familiar. And we also looked into, and we sort of talked about doing, I think it was vaguely homework, and I don't think we got to anything but the most basic form of this, and that was if we can find these 4 points, we can then do the same sort of line drawing trick and draw like a line here and a line here and one there, and sort of getting rougher as we go, but one there, just so we sort of prove to ourselves that we have those 4 points. So what we're going to do today is we're going to basically get up to the stage where we've got these 4 points, and we're going to instead of drawing it with like this sprite nonsense here, we're going to stick actual triangles like that, and so those 4 points will form 2 triangles that we can then send to the GPU and use that to draw lines, which is sort of more along the lines of what you generally do, and which is like almost identical to what Sprite Patch does. So when you like draw this 1x1 pixel texture, Sprite Patch is going and sticking triangles across that anyway, so to draw it. So Sprite Patch is doing the same thing here, but once we're drawing that ourselves, we'll be able to do cool things like we could stick some end caps on that, and like it would look like that, and then maybe we could texture those end caps so we've got like a a nice sort of circular end, so our lines look nice and pretty, like like that. So that's sort of where we want to go today, and we might not get up to too far into the circle bits, particularly because I want to do pixel shaders for that, but we should at least get some of these triangles drawing on the screen. So let's have a look at some code. So we had this working, we got our thing, we can draw some lines, so that's all fine. So the first thing we want to do is we want to basically get a triangle drawing on the screen, and what this is sometimes called is like a black triangle, and the idea is you have and this may be a good reason to change the background color that we're using to like something more something that's not black, just so that if we happen to draw a triangle and we screw up the colors, for instance, we can still see it as a black triangle, just to be sure that it's working. So let's go to load content. So we're going to need a few things, and I'll just draw them out on here. We're going to need a shader, which in XNA and FNA is like an effect. We're going to need a vertex buffer, and we're going to need an. Now, do you remember, certainly, like, hopefully you're familiar enough that you have a rough idea what that does, but this stuff here, we did talk about it briefly previously, so are you comfortable with those two concepts?
Let me try to remember. I think the vertex buffer is basically where you're storing I know that the index buffer is just pointing to vertexes you want to draw
Yep.
at a given time, right?
Mm-hmm.
That just makes sense. It's an index buffer. The vertex buffer, I mean, I want it to be a long list of vectors, but I could be
Yep.
wrong because I mean that would be in two-dimensional space, right? So
Well, well, this is sort of like vertex buffer can have all kinds of data in it, and we're going to sort of look at some of that today. So if this is our vertex buffer, it's like, here's vector, 1, 2, 0, and here's 1, 3, 0, and like so on. And perhaps these will point at like these things. So it's like this is 0, and this is 1, and this is 2, and this is 3, and so
right. And then if you want to draw like that box, is sort of like the index is like 0, 2, 0. It was 2, 3, 3, 1, 1, 0, or whatever the direction is, right?
yeah. So you'll see that certainly if we're drawing triangles, each sort of triplet of indices in the index buffer
Right.
points at a triangle. So it's like here's 0, there's 1, there's 1, and then so on up in here.
Right. And then this is up to us, or this is sort of, I think you were saying that it's sort of like the Carmackian convention where you just do it the way it tells you to, like in terms of order.
Okay, so there is the
I remember left to right versus right to, the winding is
order.
one of them.
So this is clockwise. You'll notice that I've done all these, and we'll have to make sure we're matching what the effect is expecting. We can actually set the winding order, and I think I showed you this the other day, that we can set it to like clockwise, counterclockwise, or both, and everything that is
Right.
sort of I think clockwise is the standard one. So what you'll see is like col mode dot counterclockwise. I think that's spelled out. And what that means is it will cull everything that's counterclockwise. So if we want our triangles to actually appear on screen, we need them to be clockwise, and vice versa. And so and then the data we put in the vertex buffer, it could just be positions, but it could be more than that, and we'll get to that very, very shortly. So let's tell you what, because we've been talking about it, let's start with the vertex buffer and the index buffer, and we'll do the shader next, because that's quite quick. And this is just API stuff, really. So come up to load content, and we'll have a few more things. We'll have a vertex buffer, and we'll have an index buffer. And there's probably, those names will do for now. And we'll just create them. So VB equals new vertex buffer, vertex device, and then something, and then how many vertices we want. We're going to draw a triangle for now, so we want 3 vertices. Okay, so you'll notice I've left this one blank for now. And we'll make the index buffer. New index buffer, device, index element size. That basically means, do we want 16-bit or 32-bit vertices? So we'll go 16-bit for now. Actually, I'm trying to remember if there's a compatibility issue. I can't remember. 16-bit bits will do, and if we lose a bit of performance, we're drawing one triangle, so it doesn't matter. We want 3 indices for a triangle, and we're going to put it right only. So this is basically whether our index buffer is going to be uint, or I guess if to spell it out for people who aren't familiar with C#, is it uint32 array, or is it a uint16? And so that's what that determines. And obviously we can just use the short form. So uint is 32 bits and short is 16 bits. So we'll go with 16 bits for now, and we'll fill that in a moment. So let's come up here and talk about, actually, you know what? We'll finish the index buffer. Let's finish the index buffer, because we know that we just want the most stupid, straightforward, dumb, obvious index buffer possible. So it's just that, and then set data. And so hopefully that should be super obvious. Just like nothing should confuse you about that.
No.
Excellent. Okay, so let's come up here. And we've got this field here that's, it can be a type or it can be a vertex declaration. I want to say that using the vertex declaration directly, yeah. If we use a type, that's like a, a C# type, that goes off into it's system. It's not even system.reflection, but if we use a type, that is obviously going to take a bit of performance and it only happens once, so it's not a big deal, but it's going to go and try and resolve that type and look up a thing that I'll show you in a moment. So what we want is a vertex declaration, and fortunately when you make these things we kind of already have it. And so I'm just going to actually, let's see. No, I'm gonna do a little thing over on the whiteboard here. So as I was saying, I'm gonna introduce a little thing. We have, this is vertex 0 over here, and it's got a position, but we can add other stuff to it. So we could also say that it is that, and it's red, and maybe this one is green. So we're just adding a color. So if you remember that color in XNA is spell it the American way, is a struct which has like a uint packed value. So it's a 32-bit value that represents red, green, and blue. So this entire structure here, this position and a color, is one vertex. So does that make sense so far?
Yeah, other than I thought there was an alpha channel on the color.
Yeah. So this is uint value, so that's 32 bits. And that's RGBA, and each of those is 8 each.
Right.
So and
Which people mistake it's 8-bit color, but it's actually 8-bit per channel, so it's really 32-bit color.
Yep. So and because we're using FNA, we can go in here and actually look at it. So it's public properties. B is a byte, 8 bits, and it goes and gets the packed value, and this packed value is the only data member here, and it's ARGB. So. Alpha is the most significant. So yeah, the diagram where I say RGBA, it's actually ARGB, because obviously that order is important if you're packing it into that
right
value. So
I see. So the order only matters because of where it's being slotted in the bit fiddling.
Yeah. So the graphics card is going to go ahead and it's going to say, all right, I want to draw this out to the monitor. I need to know which is which, so it should actually be ARGB, and when it goes to do like an alpha blend, it's going to read from the top most significant part of that 32-bit value. In fact, what it's going to do is actually will take that 32 bits and it will spread it out into a floating point register, so it'll actually become like 128 bits or something, depending on the graphics card. Okay, so as I was saying, we wanted a position and a color, and fortunately XNA and FNA come with that data type built in. So we want a vertex position color, and so you'll notice that when I type this in, we have a few variations. So we have vertex position color, we have vertex position color texture, we have normal texture, position texture. So we actually have all these combinations already built in that we can use. So just grab position color for now, but eventually we'll want a texture coordinate as well, which is what FNA, XNA uses. It's like, I want to know where I'm going to map my texture. In this case, it's a 1x1 pixel. It's like this is 0, 0, and this is 1, 1, and so on. And obviously this is like the variations on that, like 0, 1. And so that's how it figures out where the texture is going to appear when you draw it. So for now, we'll just go with color. And obviously we want an array of these. We don't need, yeah, we need that. It's formatting it nicely. Need that and that is an interesting way to format that, but sure. So what we're going to do is the same thing we were talking about like last week, and that is we want to get something really dead simple up on the screen. So if you remember, I might just make a new layer for this. Okay, so our screen kind of looks like this, and we have like 0, 0 in sprite coordinates, and like, you know, width, height is that coordinate, and you know, we have like a red line here and like a green line or whatever. I think it's blue, it doesn't matter. Anyway, so we want maybe to draw our triangle, say here. So we need to know what these points are. So from memory, I think this is like 100. This is 200. So let's stick the Y position at 250 here, and that can be like 350. And I think that can be like the X values can be 50, 100, and 150. So we're just figuring out, you know, where do we want our triangle to show up? So hopefully that makes sense. So position equals new vector 3, and you're way ahead of me, and you've done the right thing with the colors, and that is let's know what our RGB is. So color.red. Does that have a constructor?
Yeah, I just use the constructor one. It doesn't matter either one.
When in my test, I had trouble actually getting the constructor to autocomplete. I think I don't know how that happened. Anyway, green and blue. So as I was saying, you know, we want our vertices to be clockwise ordered. So you know, that's that way. So this is going to be 0, 1, and 2. So let's punch those numbers in now. It should be fairly straightforward. So 250 at the top for the Y, and 100 for the X. So 100, 250, and then this one would be going clockwise would be 150, 350, and then this one would be 50, 350. So and of course they're vector 3s, so they need a Z position, which can obviously be 0.
I wonder why it's choking on the. Oh.
Yeah.
They don't have a default one, eh? It's constructor with 0. I guess they make it explicit.
Yeah,
Right.
it's exactly for that. Anyway, so now we have our vertex position color. We're going to come up here and be like, well, what are we going to do with this type? We could go type of vertex position color, which will go and do some magic within the API. But fortunately, all of the built-in ones, and any one you make your own, should have its own vertex declaration provided as a static member, and that may be what the reflection thing looks for anyway. I can't remember how that works because I always do it this way. So there's our vertex declaration. Let's go and have a quick look at what that is. So I'll let you catch up.
Oh, whoops.
Yeah. So it's a static member.
Basically, like what type of data we're trying to throw into the buffer.
Exactly. So vertex declaration here, there's the static constructor that's going to construct this thing. It's like, all right, vertex declaration, it's an array of elements. So here's the vertex element. And so there's 2 elements in here. One of them is a position and one of them is a color. And you'll see that vertex element is like, you know, what's its offset, what's its format, what's its usage index. So I'll just jump ahead to the pixel shader bit and be like, right, well, when you get in here, like there's color 0, text coordinate 0, This is a pixel shader, so it doesn't have a position, but there's also, like, if you have a vertex shader, you'll get like position 0. And what happens is, like, who's calling this? Well, the graphics card's calling it with data that you passed in these registers. What are those registers? Those registers are vertex elements, basically. And so for this one, at offset 0, there's a vector 3. So that's 12 bytes. So the next one is at position 12. So that's that's 3 times. There's 3 4-byte, 32-bit values that are floating point vector 3. And that, if you mouse over that, it explains that. And then what is it? It's position. So, like, we can go to the usage and we can have, like, position, color, texture coordinate, normal, binormal, tangent, blah, 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 blah. But we've specified that it is coming in the position register, and it's coming in the 0th position register. So,
right.
In the case where maybe we wanted like more than one position or like more than one color, we could I know I'm modifying FNA here, which is not great, but maybe this could be at 16 and we could have color 1, for example, if we wanted to add another color there. The other important thing, obviously, is that when these get passed in, they get blitted in. Does the word blit, are you familiar with it?
It's like my only understanding of it is it's basically direct access to RAM and, like, dumping it in
pretty much
somewhere.
Pretty much.
Space.
It's a direct memory copy. So in fact, you'll notice this is serializable sequential with pack 1. And so what you'll find is that these are the the fields of this struct is position and color, and so the offsets listed here match the offsets in memory of that and that. So what happens is, we go off over here and we've made an array of these things, and so you'll find that the format in memory is like, right, well, here's offset 0 is a vector 3 that's a position, and then offset 12 is a color, which is red, and that's 4 bytes and packed in that particular way. And then then we go into the next element, so it's like, so that whole thing is 16 bytes, and so then the next one starts, and so 16 plus 0 and 16 plus 12 is the same data at those offsets, and so on. So that's basically how you're communicating to the graphics card what the heck you've just told it, because otherwise this is just a random stream of bits.
That's right.
Okay.
That makes sense. I mean, it is literally a buffer, so you have to define the structure of the buffer and what data is in it. And
because so obviously C# knows because we're programming in it, but the graphics card, no idea. Finally, we'll just VB. You're already way ahead of me, which is good. Set data. So the last thing that I said we needed was a shader. So let's go in, and for now we're just going to use basic effect. Later on we'll make our own shader, but for now basic effect equals new basic effect graphics device. Now the thing about basic effect, and like if you're really keen you can F12 on it and go and read all of it. It does a bunch of interesting things. But basic effect has various different shader effects in it. So some of them want a color, some of them don't want a color, some of them want a texture, some of them want lighting information like normals and stuff. So we need to turn those on and off. So from memory, is basic effect dot texture enabled is false. We'll turn that back on later. Effect dot vertex color enabled equals true because we have vertex colors. Basic effect dot lighting is false. Fog is false. Those are the only 4 things. Okay. So that configures the particular effect that we want. So that's all fairly straightforward. Anything confusing so far? Excellent. Well, that's great. We can just blast on through to here. So, and I mean, I guess this is kind of revision because I've sort of mentioned a whole bunch of these things before. So I'm glad that you're remembering them. So the next thing we want to do is like, how are we going to set up our camera? In fact, what we'll do, we'll jump past the end of our old style drawing with the Sprite Patch, and we'll start down here. Because if we did nothing, you'll recall that basically we want this arrangement here with 0, 0 in the top corner and width height in the bottom right corner, and we this is how Sprite Batch defines it, and we can define it that way too, or pretty much any other way we can think of, as long as it's a linear transformation, which we've been talking about. And so the way the GPU renders is in a box that is, and I think this is right, a little bit from memory here, -1, -1, and that is 1, 1. So, and then so obviously that's 0, 0, and on the z-axis this is like z is from 0 to 1, so it's kind of like a half cube. I'm not sure exactly why the z-axis goes from 0 to 1, whereas these ones go from -1 to 1. So, but that's how it does it. And so if you have a point, if you have a triangle in this space, it doesn't really matter. It could be 3D, it could be whatever. It will show up. If you have one that's like, I don't know, that's not a very good triangle, but if it's coming outside that space, the GPU will like, clip it off and just draw the part that appears in this space when it goes to rasterize it. So when it says, okay, I've got these triangles, I'm going to go ahead and find all the pixels where those triangles appear. It only draws pixels that are in these coordinates. So what we need to do is we need to get from this space here down to this space, and fortunately FNA and XNA have a built-in mechanism for doing this, and we'll look at that now. So oh yes, and so this is the projection. So we're projecting from some kind of space into the rasterization space. And that's just what that's called, and we'll look at the other two spaces in a second. So basic effect dot projection equals matrix. So this is our XNA matrix. Create orthographic off center. And so if you look at the parameters, you kind of get an idea of exactly what is going on here. So we've specified our what are the parameters? It's like this is left, this is right, and like if you pretend it's 3D, this is near, and this is far. And so you'll see that this forms a box, and we do a linear projection to smack it down into that box. So and because we've done a whole lot of that, hopefully that makes plenty of sense. So we just basically blast in those values. So we want the left to be 0, we want the right to be so we need the viewport. So viewport vp equals brackets class.viewport. We want the bottom to be the height, and we want the top to be 0. And then near and far, I usually go -1, 1, just because. But I think some people just go 0, 1. It doesn't make much difference. Orthographic projection. Hopefully, the word orthographic is familiar to you.
I think of it like when you want to view a 3D scene on its side two-dimensionally, right?
Yeah, exactly.
You're
So
killing a plane and just
exactly. So
right.
if you've used like a modeling program, you'll have like the 3D view and stuff, but then you usually have like X, Y, Z views, and usually those will be orthographic. So the all the, I guess, lines are parallel that are parallel in space. Whereas like if you're doing the other projection I was talking about, parallel lines in the world will converge or diverge and stuff because the view frustum looks more like that. That's a horrendous drawing. Oh, that was bad. So anyway, yeah, like stuff further away will appear it will appear smaller because that size circle,
Right.
that size circle when you project it onto that thing and so on. I think I talked about that previously. So yeah, and so you can also see that like if we wanted, because as we've been saying, like this space here, this like client coordinate system here is really annoying when you're doing like say physics-based games and you've got like a platform and you've got a dude standing in your platform and you'd really like gravity to be going down in the y direction. So we can just change what the bottom and the top. Obviously, if we do that, we then have to think about the fact that now we have to change what direction our winding order of our triangle is because we've just flipped the world, but that's how you do that in a sort of very straightforward way. So we have our projection matrix. The other two matrices for now, effect.world is we'll just leave those as the identity matrices, but
Are we going to plug our camera into that view one at some point?
we will do that right
Oh,
up.
I didn't even see you putting into your camera.
Oh, no, I'm just swift on that one. So, and the way these works is these just apply sequentially. So it's like world, view, projection. And then typically you'll use world to place the model in the world somewhere. You'll use view to move the camera around. And you'll use projection to like figure out how the camera works, I guess, is the best way of describing it. And let's just have a quick gander at the source code because we can. What you'll find is that we set the projection matrix, and so these are the matrices you're going for. But this worldview one, and I haven't actually looked, so I'm just hoping this is correct. Set worldview and project fog ref. So there's it does a whole bunch of things, but basically it spits out worldview project as a matrix. I don't know why it's called world view here and worldview project elsewhere. That's interesting. Maybe it does something a little more complicated, but certainly for the world and the view matrices, you can see that what it does is it just does matrix multiplication, combines those into a single transformation. So when the vertex shader is doing its thing, for every vertex, it doesn't have to go that times that times that times the vertex. It just does that times the vertex. So it's obviously a lot faster. So that's just,
that's stuff that we did too when we were doing our work.
Exactly.
We were combining matrices.
Exactly. So and it's just an optimization, hoisting out the common calculations. Yeah, so we've got our effect. Now it's all set up. We have our buffers. Now it's just a matter of using them all together. So the way this works, and this is just some API nonsense, it's like for each pass in basic effect dot current technique dot passes. Now some people, when they come to this, they'll just do this. They'll just go passes index 0 and just use that directly. And we could do that because we know there's only one pass. But if you're making complex shaders, and particularly if other people are authoring the shaders, maybe there's more than one shader pass, and so the whole thing gets rendered multiple times. So we'll just do the canonical thing for now. But
Sure.
sometimes you might want to adjust that. So it's basically pass.apply. And let me check my notes. Checking my notes to make sure that I remember what this does. Yeah, okay. Okay, so it's simple as this. It's graphics device dot set vertex buffer, which is the vertex buffer that we made earlier. Graphics device dot indices equals index buffer. Now you'll notice you can set multiple vertex buffers and one index buffer. And the reason for that is you could have multiple data streams. So, and maybe it would be useful, like over here where we have, we've got a position and a color, maybe those are in two separate buffers and we want to be like, here's the list of colors, here's the list of vertices. So that's just a different way of sorting that data out. And then finally, graphics device dot draw, and there's a few different options here, but we're going to go with draw index primitives. And so now we get to specify the primitive type. So you'll know that I talked before about, we can make a triangle strip, for example. You can't do a triangle fan anymore. I don't know, probably because no one ever did. But we have a list of triangles, which is what you typically will do.
Yeah, I was just wondering what this ext one was. That must be an FNA thing.
Yeah, so that it probably was the case that it wasn't in DirectX 9, or it was not widely supported in DirectX 9, so they didn't put it in XNA. But it is the case that you can draw a list of points, and there's some things with like the GPU can draw sprites, something like that, from just a list of points. But there are some caveats with that, so I'm not particularly familiar with how that works.
Yeah, no worries.
Exactly, but basically it's like saying, okay, my list of indices don't consider this block of 3 a triangle, consider them each individually, basically. And if you do a line one, it's like, well, the first 2 is a line there, and the next 2 is a line there, and the next 2 is a line there.
These are basically just conventions for a data format, really, right? That's
exactly. It's basically saying, how are the indices grouped, and
right.
How do you want to interpret them? So base vertex, this is all just like, what's the starting index? Number of vertices, we have 3 vertices. Start index 0, and primitive count 1, because we have one primitive.
See, I had that already, except I had 00303 because I thought we had.
So the primitive type triangle list is like there's 3 indices per primitive, and so we have 1 primitive times 3 vertices.
Okay, it's not how many times we're drawing a triangle. It's just how many primitives are included in this list.
I think there are some tricks. I can't even remember them or think why you really want to use them unless you're getting involved.
Well, maybe you'd have 6 pieces of data in the triangle list, but it was only for 1 primitive. But if you could put 6 and 2, and then you'd have 2 triangles for the same.
Yeah,
right?
So you could have 6 and 2. You could also have, it would be a bit stupid, but you could have 3 and 2. And I don't know, maybe you're just drawing the triangle twice. Maybe you're not you never do this in a real game, but maybe you're not sure what your winding order is. So it's like, well, there's my vertices, and I want 0, 1, 2, and then I want 0, 2, 1. So
right.
And then
it's up to you and what you're doing. Yeah.
And so then you pass 3 vertices in, but 2 primitives. So basically, there's a whole lot of trickery, because we're basically have I guess a whole bunch of data, and was like telling the GPU how to interpret it, and I guess these are the things that the GPU finds, can handle, I guess. So why don't we run that? That's actually a good idea. Let's run that and see what happens. I get a triangle. Let's see if we're in sync.
It's beautiful.
Gorgeous. Gorgeous, gorgeous, gorgeous. So this next part is real simple. and that is, why don't we come down here and we just slam our camera in, which is as simple as camera dot as x and a measures, because we created that one earlier. And now, in theory, we should be able to drag our triangle around and zoom it, and it just works perfectly.
Makes me happy.
So this is the wonderful thing about this, and maybe at some point we should go ahead and make like a new file for it, because now we have a transfer.
Mine's gone. Mine's gone.
That's not good. Does it?
What did I do?
Did you scroll? Just checking you didn't like scroll it off screen or zoom it too far out to see.
Yeah, I'll try again.
Yeah, it's fine.
Oh.
It's fine.
Okay. It's pretty up close. All the nuanced patterns.
So
now who decided to do this gradient? Obviously the GPU decided to gradient blend our points.
yes.
So why did it do that?
So that's a bit of an in-depth topic. Maybe I'll link an article to that. But basically what it does is, I guess, exactly what you would expect. Like it. So we have 3 points, and this one is like, so it's red. So this is these R, G, B triplets, and it goes. This will be 1, 0, 0, and this is going to be these are different to what we actually drew on screen. Never mind. So this is going to be 0, 1, 0. And this one is going to be 0, 0, 1. And so we have our triangle, and whenever the GPU goes to draw a pixel, it does an interpolation. I'm trying to remember exactly the terminology. There's like barocentric coordinates and all sorts of fun stuff involved here. But the obvious thing that it does is like, well, okay, I'm going to draw this pixel here. Where am I in this triangle? So I've got 1, 2, 3. Let's do an interpolation. So I'm somewhere along, this line here, I'm way away from this one. So this end result is going to be like 0, 0.5, 0.5. And then if you, if we're this point in the middle here, and obviously I should mention that dot green is not the same as lime. So if you actually want that color, you need to change that to lime, just because that's how it's named. But if you have this point here, obviously it's going to figure out how far away it is from each of those, relative to like that line. So it's like that far, and then that far and that far, and it'll do some calculation, and it's like it's going to be a mix of all three colors. And obviously,
that makes perfect sense.
If let's change
it. We provided this polygon with 3 different color pieces of information. There's no way to reconcile that unless it's going to interpolate it. It has to do something with that.
Exactly. And you can. I'm not sure. There are ways of changing the interpolation mode, because it does this for like everything. So if you have a 3D model, for example, let's find some blank space. So if we have, we've got, a triangle, amazing art skills. We've got a triangle here that's part of like some, surface. So, you can imagine that those are other triangles going off into the distance, worry about that. But this triangle here is the one we're going to think about. And we want to do some lighting equations. And so what we want to know is, like, if we have a light up here and it's shooting down there, and maybe the camera's up, the camera's up here looking this way, we want to know how it bounces off this surface. And to know how it bounces off this surface, we need to know basically the perpendicular to the surface, which is called the whoops, oh no, what has happened? Can I have my paintbrush back, please? Let's call the normal.
That's right. Yeah, we covered perpendicular and the normal.
Yep.
I mean,
so
already, yeah.
And so that's why it's called that. And so if this was like a smooth model, it might be the case that that normal is pointed out that way, and that one is pointed out that way, and then this one is pointed out that way. And so if we're hitting in the middle, we want this surface, even though we're drawing a triangle, to appear sort of slightly curved upwards. If this is like, you can imagine this is like, you know, a ball or a sphere made out of triangles.
Jeez.
I thought you were about to say a geodesic or something. It's just like, oh yes.
No,
I think that might be the proper term for it. It's a certain.
It sounds like it. Yeah.
It's like there's various ways you could chop it up into triangles, and that's one way that leads to quite nice triangles. But yeah, so if you want to know the point in the middle, and so the way the light will bounce on it, you know, you'll get this like nice. You know, if you're doing specular lighting, you'll get this nice, you know, specular spot that will be more or less circular because, you know, it's interpolated. Whereas, you know, if you didn't interpolate, and that's like a mode that you can, actually, no, it's not a mode you can select. You, because I think it always interpolates. But if you had them all pointed straight up, you know, they'd all interpolate to the same value at every point on this thing, and like it would. Light up each one, and it would look, you know, it would look faceted, and you could see that as it reflected the light. So that's sort of a rough thing, and so every one of those parameters, obviously except position, because that's, I guess, position, but every one of those parameters where it's relevant can be interpolated. So normal, texture, texture is obviously another one. It's like we come up here and we're like, what have I done to this canvas? We come up here and it's like, how do we figure out what pixel to draw like there? It's simple. We interpolate between our texture coordinates, and it will tell us, you know, that part of the texture. Like, so, you know, 0.7 might be the thing, and it goes off into the texture memory. And if this is like a 256 by 256 texture, it'll go and pull that pixel. And in fact, it will pull like 4 pixels and do bilinear interpolation and all sorts of fun stuff on it. Can I put this back now? There we go. Close enough. Okay, so now we have a triangle on screen, and we're kind of short on time.
That's okay. I mean, this is good. We can always do the perpendiculars. That gives me some time to review the perpendicular code we were doing before with the boundaries around the triangle bits.
So,
because we're going to need that anyway, right?
We are going to need that. So there's a few. It's like, is there anything else I want to quickly cover before we sign off? So, the only interesting thing is like this is a buffer of like this is like a fixed buffer.
Right, we haven't made it interactive yet.
And we're going to want to dump stuff into that buffer and actually do some complicated stuff with it. And there exists dynamic index buffer and dynamic vertex buffer. Oh, it's raining. Maybe a good time to sign off. Anyway, so
I didn't know it rained there.
It's been raining for weeks. It's actually quite nice because it should be really hot in the sort of the middle of November, and it's quite cool. So these are sort of equivalent to, you can imagine if you have a I'll leave a full explanation of this to later. So what you can look forward to is we'll talk about how the GPU how the GPU sort of handles that and that and that and that in sort of different ways depending on what you specify there, and why we might want a dynamic one if we're going to be like changing the contents of that buffer. Although obviously the obvious explanation is because the API documentation says to do that. Yeah, I think we'll call it there.
Okay.
All right,
cool.
And where's OBS? All right, see you everyone.